this computer. Okay, so I was saying the first set of homework is these problems, standard problems at the end of chapter 1 in the Rybicki Enlightenment textbook. Further on, I'll put the homeworks in my lecture summary. But for now, for this chapter, the book has standard problems that you should know how to solve at the end of the first chapter. Okay, so
all of the problems in the book, or some of the problems?
All of them. I think.
Okay.
I think they are solved at the end of the book, if I'm not mistaken, if I remember well. But you can find the solutions over the internet, I'm sure. But it's just that you need to go through them. Okay.
Okay. Thank you.
Okay. It's not that many. It's like 10 problems. But you might want to get started. The idea also is to solve this homework to prepare yourself for the first exam. And this exam will happen when we finish the first chapter. So I'll ask if everyone is ready to solve the exam, and it's going to be fairly easy. I mean, in the sense that you'll have a whole week and I'll give you references, and the only thing that matters to me is that this is a personal work at the exam itself. Okay, so I'm scrolling back to where we left it. Thermal radiation, mean free path, the optical depth, emission only. I think this is where we were at. Okay, so yes, we talked about the absorption. Okay, so that's a nice drawing where we see, well, the ray traveling from left to right in the figure 17A. And this is what the ray would see of the medium is traveling through. And so there are obstacles that can absorb the photons traveling in that direction. So in the end, when we have both processes of emission and absorption, the radiative transfer equation is then cast into this form. Do you have any questions so far on this topic? No? Okay. So for okay, so then the textbook talks about well, limiting solutions, solutions in simple cases. For instance, if there is only emission, then this can be trivially integrated to yield the specific intensity as a function of the boundary condition at some point where ray hits the medium out to a position S along the ray. Okay, you can solve this as long as, of course, J nu does not depend on I nu. Now, if you look at the equation 24 in my lecture summary, you can see that this term, J nu scattering, is similar to J nu connected to the absorption. But this term is complicated. It depends on the incident intensity. So if you include scattering, then you cannot solve this directly. Okay, it becomes an integral differential equation. I will look at ways to solve the radiative transfer, including scattering, in an analytical solution, or even though in the case of isotropic scattering only. So for absorption only, we have this other solution. Okay, so in this case, again, the absorption coefficient is assumed not to depend on the incident radiation field. this is not always the case, but for instance, when we solve radiative transfer for lines, then this absorption coefficient could depend on stimulated emission, and this often you could be negative and depend on the amount of radiation impinging on the target. So alpha nu itself could depend on I nu as well, as is the case for lines. So this is only an idealized situation where the best way to think of it is when we are looking at interstellar extinction. For instance, you are observing a star in the Milky Way, and the star lies along, is close to the galactic plane. And so you have the standard rule of 1 magnitude of visual extinction per parsec. That's kind of more or less the rule. So this visual extinction can usually be modeled just with this standard absorption only. And so basically this term here would be the exponential of the extinction magnitude. So this leads us to the concept of optical depth. Okay, so optical depth is defined as the product of the absorption coefficient times a depth. Okay, a physical linear depth. So both things are called the optical depth. Okay, so this is a very important quantity, and it is frequency dependent, of course, since alpha nu is also frequency dependent. Okay, and so maybe at this stage, one of you would like to help me out with describing the textbook a bit more. Or if you haven't, maybe this is all clear to all three of you.
Okay, so Professor, I will try them. Yeah.
That's great, Pratyush. Let me make sure that now you can share screen. If you want, you can share screen.
Yes, just yes. Yeah. So is my screen visible?
Yeah.
Yeah. So as Professor defined that how this optical depth is related to absorption coefficient, d tau nu equal to alpha nu ds, and when you integrate over a certain path length, you get the optical depth of a certain path. And so this tau nu, which is optical depth, helps us to understand what is the nature of medium, whether is it optically thick or optically thin. So what does that what it does mean is that if the medium is optically thick, then the most of the light that is coming from a certain source will be absorbed by the medium. And when the medium is optically thin, most of the light that is coming from the source will be passed from that medium as it is, or maybe a certain level of absorption could be there. It depends on the value of this tau nu. So generally, to classify the medium, we say that if tau nu is greater than 1, then that medium is generally referred to as optically thick or opaque. And when this tau nu is less than 1, then that medium is termed as optically thin or transparent. So as the professor rightly said, that this tau is dependent on mu. So so it says that if suppose the medium is optically thick and tau nu is greater than 1, so whatever light that has frequency nu will be absorbed by the medium. So
So,
that is
Patrick,
the
here is an important thing I wanted to comment upon. The distinction between optically thin and transparent is based on this criterion whether tau nu is greater or less than 1. But in practice, nowadays, people talk about an optically thick medium when the optical depth is much greater than 1. So when the optical depth is around 3, 4, 5, 10 more, that's optically thick. It's more like a limit when it's much greater than 1. And it's optically thin when it's the opposite, when the optical depth is much less than 1. Now, it turns out that when you have something observable, usually tau nu is close to 1. But when you see something, like for instance, the photosphere of a star stems from where the optical depth is 1. That's the definition of the photosphere. So the light you see from stars comes from where the optical depth is 1. Okay. Likewise, when you look at the interstellar medium of galaxies, anything you can see is detectable because tau nu is of order 1. So these two cases, optically thick or transparent, thick, are limiting scenarios. Okay.
okay. So even if we say that we are able to see the photosphere of sun, then there is certain absorption also going on, because tau nu is equal to 1. So there could be a certain absorption. It's not transparent that everything that is coming from the sun will be received by us on that.
No, that's correct. The sun is very opaque. The sun, we agree. If you integrate the optical depth from the core of the sun to the observer, if you integrate over the whole envelope, then it's massively optically thick. Okay, but what I'm just saying is that the radiation we get in the end from the photosphere to us is tau nu equals 1. Yeah.
Okay. Yeah. So the next step is to write the radiative transfer equation in form of optical depth, as it is easy to understand the equation. So what author has done is he has introduced another term known as source function S nu. So when you write the radiative transfer equation, what is written in 1.3, question 1.3, d I nu by ds equal to minus alpha nu I nu plus j nu. So if you divide this equation by alpha nu, so then the equation becomes d I nu divided by alpha ds, so that will become d alpha nu by d tau equal to minus I nu plus j nu by alpha nu. And this j nu by alpha nu is what the author is telling as S nu as a source function, which is just a ratio of emission coefficient to the absorption coefficient, as you can see. So this is another form of radiative transfer equation, but now in terms of optical depth. Earlier what we were getting was in terms of physical depth of the column that was seen, and as he has written that the source function S nu is often a simpler physical quantity than the emission coefficient. Now the author wants to derive the solution of this radiative transfer equation, whether it's in the form of equation 1.27 or in 1.23. So he did a mathematical trick. So he again introduced two different variables, capital or italic I, whatever, a capital I, let's say capital I and capital S, and he uh, he uh, uh, he wrote the value as it's mentioned. So this capital I is function of optical depth, and this capital is also a function of optical depth. And then when you put this value in the equation 1.27, so you will end up with this a form. If you try to do, it will come into this form if you derive to see if, how this form has been arrived. And then later he the other integrates, and then we get the final solution of this transfer equation. So he just put back the original value in the in I new terms and S new terms, and this is the final solution of the transfer equation. And here the author has mentioned that this equation 1.29 can be interpreted as the sum of two terms: the initial intensity diminished by absorption plus the integrated source diminished by absorption. So so there could be some initial radiation already coming into a certain medium, so it will get absorbed, plus whatever emission that is generated within the medium will also get absorbed, as it will pass through certain optical depth or certain physical depth. And then he derived a specific solution of the radiative transfer equation, where he considered that let this source function should be constant, and when the source function is constant, so it will come out of the integral, and what we will get is something like in the form given in question 1.30. So I nu T nu equal to S nu plus and yeah, so, and then
I like the first form. I knew the first line is more the standard one, the standard way to put it.
this one. S.
Well, yeah, 130. Just a first. I mean, we will see this one very often. So this is the solution to the radiative transfer equation without scattering, and for a uniform medium where alpha nu and J nu are constant, are constant with position within the medium. So that's a very important solution. Okay. Do you want to continue a little bit more, Patyush? Or...
Yeah, so I will end up with this last paragraph. I would like to read the whole paragraph because this is an important understanding that we should remember to visualize this equation. So the author says that we conclude this section with a result of use later, which provides a simple physical interpretation of the source function and the transfer equation. From the transfer equation, we see that if I nu is greater than source function, then d I nu by d tau will be less than 0, and I nu tends to decrease along the ray. So if you see this equation, so if suppose I nu, yeah, suppose I nu is greater than S nu, so this whole term will become negative. So so this d I nu by d tau nu will be less than 0, and this I nu will try to approach the source function, And similarly, the other way around, if I nu is less than S nu, so this S nu will be so this whole term will be positive, and therefore di nu by d tau will be greater than 0. So now this I nu will decrease. Yeah, I nu will so this time I nu will increase to reach the source function. So this is the interpretation that author writes. So again, I will read. So from the transfer equation, we see that if I nu is greater than source function, then d I nu by d tau nu is less than 0, and I nu tends to decrease along the ray. If I nu is less than source function, then I nu tends to increase along the ray. Thus, the source function is the quantity that the specific intensity tries to approach and does approach if given a sufficient optical depth or physical depth. In this respect, the transfer equation just describes the relaxation process.
Yes.
So yeah, so I will end.
Well, Pratyush, thanks very much. I can share screen again.
Yeah.
So yes, thanks for insisting on this last point. I think it's a very important one. We'll see shortly that the source function is the Planck function in the case of thermal interactions. We don't always get thermal interactions. For instance, synchrotron radiation is non-thermal, and the source function is not the black body law. But usually, in most circumstances, S nu is the Planck function. So in the end, the specific intensity emerging from a medium has as a limiting value the source function or the Planck function. It can never be a greater, and it can never be, but it can be less. I mean, it can be less if there isn't enough optical depth. Okay. I don't know about whether you have any questions about the mean free path and what's going on the radiation force. Okay. Would maybe Felipe or Andres would like to comment on or to have any questions about the mean free path?
No, I don't have any questions on mean free path.
Okay.
I can talk about it if
well, if it doesn't bother you too much, Felipe, that'd be great. I mean, to do this together. Yeah, I mean, it's just the mean free path is the usual definition. I mean, you know the usual argument for the mean free path of a you know, I mean, it's the standard definition of the mean free path. I think you all know that. No, I mean, is anyone not familiar with the mean free path? Pratyush, are you okay with the mean free path in Iguinegas?
Yeah, I'm okay.
Okay. Well, then maybe Philippe, if you can just summarize what's in the textbook very briefly.
Yes, sure. So the mean free path is the average distance a photon can travel without being through a medium, without being absorbed. So it's like the optical depth is related to the optical depth, and the mean free path is the distance that the photons are as the average distance between. I mean, so the optical depth is a quality of the medium, of how thin or thick is the medium, for how easy is the light travels through the medium, and the mean free path is how much the average photon can travel through this medium without being absorbed. So it's more or less the same quality, but the mean free path is a distance. It's a distance in this sense.
Yes. So there's a very important aspect here, which is the connection with the probability of absorption. Okay. So here we are pointed to equation 1.25, where let's look at it again, 1.25. So here we go. So that would be the intensity at coordinate S as a function of the incident intensity times the exponential of minus tau. That would be the, if you replace like this exponential argument here, is the same as equation 126. So you can replace the what's in the exponential here with tau nu. Okay. What I'm trying to say is this. So we have that. So I nu in S is I nu that incident on the medium times the optical depth. Okay, so that means that modulo constants. This means that the number density of photons with that frequency at coordinate S is equal to the number density of photons in coordinate S0 decreased by this amount. Okay, so this is like that would be here the fraction of photons absorbed. So that would be the fraction that of photons that has been absorbed in between S0 and S. Okay, so you can think of this as the probability for a photon to be absorbed. Okay, so if this term goes to this is actually 1 minus the fraction absorbed to be correct. But if this term goes to 0, then there's no photon left in the end towards when where we observe. So we can see that in the optically thin limit, if tau nu is much less than 1, okay, then 1 minus tau nu is the probability of absorption. Sorry, this time it's the other way around. Tau nu is the probability of absorption. Right, because when tau nu is much less than 1, this is 1 minus tau nu. So tau nu is the probability, is the fraction absorbed, is the probability of absorption. Okay. So I'm mentioning this because then in the end, when we have the optically thin limit, which is when tau nu is much less than 1, then tau nu is directly the probability of absorption. Okay, the optical depth is then the probability of absorption. Okay, so and we see that the optical depth is dimensionless; it doesn't have any dimensions. So going back here to the mean free path, when we define that the optical depth, this average optical depth be 1, we are meaning then that what is the probability? Where is that would tell us where a photon is likely to be absorbed. Okay, so of course that is no longer the absorption probability directly, because if it's equal to 1, then tau nu is not much less than 1. It's, I mean, the real absorption probability is exponential minus tau. So tau is equal, is approximately equal to exponential minus tau only on the optically thin limit. But this gives us a good idea of when the photon is likely to be absorbed. Okay, and that is also a different angle to this mean free path. you guys have questions on this, or it's pretty clear, no? Right? So this mean free path is important. Is this the mean distance that photon will travel before being absorbed? Okay, and if the mean free path is much less than one, means the optical depth is much less than one, it means that the mean free path is much greater than the dimension of the medium. Okay. Felipe, ¿quieres seguir un poquito más?
No, I'm fine.
Okay, fine. Not. Okay, so this idea about the radiation force is well, these are just definitions where we define the radiation flux vector as the same as the specific intensity, but giving it a direction. And then when we want to calculate the flux of something through a surface area, we'll take the dot product of F on a surface area. Okay. Then there is this other definition for the how does Rybik-Lyman call this? F is the force per unit volume, okay, which would be the same as the flux, but integrated over frequency and times the absorption coefficient. Okay, so that makes sense because each photon has a momentum which is equal to the energy divided by c, and so we expect that the force will be proportional to the amount of photons absorbed in the medium. Well, so there is no factor of 2 here. When we looked at the radiation pressure, we included a factor of 2, but here we're not calculating the radiation pressure on a surface, but rather the force imparted on the medium that is absorbing the radiation. So since the medium is absorbing the photons, it's absorbing the energy of the photon, and it's also absorbing the momentum of the photon. So when you have dust grain being shown upon by photons, the dust grain will absorb the heat of the radiation and warm up, and it can also be pushed by the radiation. That will lead us to radiation pressure. Okay. So in the same way as we calculated the flux of photons through a surface area, we can also calculate the amount of momentum through that surface area. This leads us to this concept of force. So it's a vector, and we need to project this on the surface area. We'll return to this later on when we particularize to the blackbody radiation, I think, later on. And we can also write the same equation as 133 divided by the mass density, and instead of having the absorption coefficient, we have what's called the opacity. So all these vocabulary depends a little bit on the textbook, but this is now a standard vocabulary that this is the opacity and this is the absorption coefficient. Okay, so I said we'll be skipping over the blackbody radiation.
Simon,
See?
a quick question. In the last two sentences of that unit, it says it does not consider the momentum imparted by emission. But when a source emits a photon, the photon also goes out with some momentum, right?
Yes, that's true,
and
Andres.
also a force.
Yes, I completely skipped over that. That's right. When you look at the microscopic process of emission, you could have the emitted photon imparting a momentum on the atom that's emitting it. Okay, so if the photon corresponds to if the transition is one given by one without a change in total angular momentum, then there is no net force, but that is a forbidden transition, as we'll see at the end of the semester. In general, when you have emission, the photon carries away angular momentum. It usually has an angular momentum of either plus 1h or minus 1h, and that leads to a recoil on the atom. Okay. However, if you take this as on average in a blob of gas, okay, if the emission occurs in any direction, then all these recoil forces average out to zero in an average sense. For a dust grain, we have many photons being emitted in a given time interval, so millions of photons, and each of their momenta cancel out. So it averages to zero for isotropic emission. But we could imagine a situation where the emission is not isotropic, and that will lead to a net acceleration for anisotropic emission. Okay, so then I was saying we had to skip over this blackbody radiation. We have well, the same as a radiative transfer, but in the case of where the source function is the blackbody radiation. Still, make sure that you understand this. Yeah, these concepts about the thermodynamics of the blackbody radiation is important because we reach this the equation of state, if you want, for the energy of a black body, Stefan Boltzmann law. It's also very important to connect it with the bolometric Planck function. So net flux emitted per surface area of a black body. All those are very important topics you should know. I think also this Planck spectrum is dead, so should have seen this in the previous courses. If you haven't, please let me know and we'll expand on this. But I think we all have, right? Pratyush and Felipe, have you seen this before?
Yes, I did.
Yes.
Okay, good. So you can work on this on your side. Properties of the Planck law, the Wien displacement law, the relationship between A and sigma. Okay, so this would be fairly new, the brightness temperature. So for Thursday, we'll we'll resume here, starting here on the brightness temperature, the color temperature, and the effective temperature. And then we'll go on with the Einstein coefficients. So hopefully on Thursday we'll finish all this topic about the Einstein coefficients, which I'm sure you've heard of before also for the Einstein coefficients. But that is really, I mean, we'll use it a lot. So this week, let's start to close here, and we'll continue again the week after next with scattering effects. Next week, I do not think I'm able to teach because of the deadlines. This is really a very stressful time for me. So next week, most likely, I will not have the time to teach, neither on Tuesday nor Thursday. I'll be writing telescope proposals at the last minute. When do you guys have holidays? Do you know?
Holidays, as in when does the semester finish?
No, you do. You normally have holidays in every month or two.
No, I don't.
I
I
don't
think
know.
we
No
had
holidays on the
I
horizon.
think we had a week, a holiday week last week.
Really? And we didn't
You mean I don't-
we didn't stop. I'm sorry for that. You should have told me.
We should have.
Yeah, of
I mean,
course.
this is all
I
new for
didn't-
me.
I
We
didn't
didn't
know.
have that in my university. So it's okay, I think.
Okay. Well, as I said, next week is going to be a holiday. Let's call it that because I won't be able to teach. Okay. So on Thursday, let's try to finish here. So please prepare the textbook up to here, and I think that I'll close next Thursday with my view on the Einstein coefficients. Okay, so this is it for today. Ciao.
Bye. Thank you.
Ciao.